The proof of the almighty power rule. Before we do the proof, I would like to do some algebra preliminaries. How would you factor a squared minus b squared? Hopefully you know this. Difference of two squares, a minus b times the quantity a plus b. Good. How about a cubed minus b cubed? A little more difficult, yay? So I'm going to factor out an a minus b, and then I'm left with a squared plus a b plus b squared. Notice that the a exponent starts to decrease while the b exponent starts to increase. Notice also that they add up to 2. The exponents here add up to 2, add up to 2 here, add up to 2 here. Also, you might notice that since it's a cubed minus b cubed, there are 1, 2, 3 terms. So let's do this now with a to the fourth minus b to the fourth. A minus b, a to the power of question mark 3 plus a to the power of 2, b to the power of 1 plus a to the power of 1, b to the power of 2 plus b to the power of 3. A to the fourth minus b to the fourth, there are 1, 2, 3, 4 terms after the initial a minus b. So now we're going to look at a to the n minus b to the n. We factor out a minus b, and we're left with a to the n minus 1 plus a to the n minus 2, b to the power of 1 plus a to the n minus 3, b squared plus ... That pattern will continue till the second to last term, which is a times b to the n minus 2, plus the very last one, which is simply b to the n minus 1. How many terms are in this second parenthesis? There are 1, 2, 3, ... There are n terms. So let's do the proof. The derivative with respect to x of x to the power of n. If we didn't have the technique, we would have to use something else. We know the technique now, but we're proving it, so we can't use the technique before we prove it. So in absence of a technique, I would have to resort back to my limit definition. The limit as h goes to 0, and then this would be x plus h to the power of n minus x to the power of n all over h. So the trick in this is that this quantity here, think of it as the a quantity, and this quantity here, think of it as the b quantity. So then this is going to be the limit as h goes to 0. Now we have to factor out an a minus b. But what would that be? X plus h minus the x, so that would simply be h. Then we have everything inside. We'll have the x plus h to the power of n minus 1 plus x plus h. Remember, x plus h is like our a, to the power of n minus 2 times x, which is like our b, plus x plus h to the power of n minus 3, x to the power of 2, plus ... And I'm desperately trying to fit it all in here. We have x plus h times x to the n minus 2. What is that? Plus x to the n minus 1. I just fit it in there. All over h. h. And then the beautiful thing happens. H cancels out with h. So that leaves us with, now what I'm going to do is distribute the limit to all the sums. The limit of a sum is sum of limits. So we have the limit as h goes to 0 of x plus h to the n minus 1 plus the limit as h goes to 0 x plus h to the n minus 2 times x plus the limit as h goes to 0 of x plus h to the n minus 3 times x squared plus dot 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 plus the limit as h goes to 0 of x to the power n minus 1. And now I need to find each of these limits. So h is going to 0. This term here is going x to the n minus 1. The next one, so h is going to 0, and we have x to the n minus 2 times x. And then h is going to 0, so we have x to the n minus 3 times x squared plus dot 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 plus we have h is going to 0, so that kind of acts as a constant, x to the n minus 1. Alright, we're almost there. You might even see it. So we have x to the n minus 1. Add the exponents here. N minus 1 plus 1 gives us, n minus 2 plus 1 gives us x to the n minus 1. Then the next one, add the exponents, x to the n minus 1 plus dot 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 plus x to the n minus 1. Now, how many terms are there here? N of them. So this is n times x to the n minus 1. QED. Therefore, we have demonstrated. And I can't hear you because you're listening to me, but I'm pretty sure you're applauding right now because that's just awesome. Now for the proof of the product rule. Alright, I need a limit definition. The limit is h goes to 0. Now we're going to have f of x plus h times g of x plus h minus f of x times g of x all over h. So I wish you could discover this, and maybe you can. I'll be patient. F of x plus h, g of x plus h. I'm going to leave some space here. Minus f of x, g of x all over h. So what I want you to do is put 0 in disguise. This is not what I want. I don't want minus 5 plus 5, although that is 0 in disguise. You're going to put something else there. You may want to press pause and see if you can figure what 0 in disguise expression will go in there. So here we go. I'm ready to ruin it for you. We're going to subtract f of x plus h times g of x, but then I have to add the f of x plus h times g of x. So now I'm going to treat this like two different fractions. One fraction is going to have this portion as a numerator, and the other fraction is going to have this portion as its numerator, and they share the common denominator of h. So limit of a sum is sum of limit. So this is the limit as h goes to 0 of f of x plus h, g of x plus h minus f of x plus h, g of x all over h plus the limit, the limit as h goes to 0, f of x plus h, g of x minus f of x, g of x all over h. There we go. And let's move this a bit that way. Good. So now, do you see what I see? A little factorization here. So this is going to be the limit as h goes to 0. I'm going to factor out an f of x plus h. And when I factor that out, I have left g of x plus h minus g of x. You might start to see it all over h. And over here, I have the limit as h goes to 0, factoring out a g of x, and I'm left with f of x plus h minus f of x. I feel clever. And so now the limit of a product is product of limits. So we have the limit as h goes to 0 of f of x plus h times the limit as h goes to 0, g of x plus h minus g of x all over h. Plus the limit as h goes to 0 of g of x times the limit as h goes to 0 f of x plus h minus f of x all over h. If you don't see it now, you never will. The limit as h goes to 0 of this particular term is just f of x, or first term. And then this you should recognize right away as g prime of x. Plus the limit of h goes to 0 of g of x is simply g of x times this here is f prime of x. Look at that, y'all. First term times the derivative of second plus second times the derivative of the first. We just proved the product rule.